Thank you. It's good to be here this morning. I want to talk about some work that myself, Ty Hostler, my PhD student, have done. And my focus here is to try to illustrate some linkage, what models can do to link some of the different areas of dust research. So we wanted to say, how can we provide this linkage between related study areas that Jeff mentioned at the first? I'm going to try to illustrate some ways the model might be able to do that. So, how do land use, soil properties affect emission rates? And Derek's talked about some of that. As did Mark. How do dust transport and deposition affect snowmelt, water quality, some of those kind of things. And so we want to actually try to have this integrating type model that can touch all these different parts of the research that we're doing. I won't go into this in a lot of detail. This is the software framework that we're using. It uses WRF to calculate meteorological conditions, land use. We update that with OBSGrid, some other things to get updated information for snowpack and land properties. CMAQ itself does the dust emission transport and deposition. It's a 3D or Eulerian-based CFD model. We have turned chemical reactions off. Those of you familiar with CMAQ, it is the EPA standard for doing air quality regulations in the United States. So we have just turned the chemistry off, which saves A, a lot of hassle in generating inputs from emission sources, and B, computational time. But one of the nice things we still do is track speciated mineral aerosols from the dust, and I'll illustrate some of that. It was kind of a pain to make this all work together, so once we figured it out after a couple years, we wrote a user guide so that it can be downloaded to help other people work through this. Dust emission, I'm going to talk about two things, dust emission and deposition today. So first, go over to dust emission, what we've been doing there. Emission rates depend on land use, type, soil composition, kind of the sand, silt, clay, size, moisture, and then that changes the 10-meter wind speed that are required for emission. And some of the previous work we had done looked at changing land use types, where we changed the size of the Great Salt Lake, shrunk it to see, okay, how did that affect the different dust emissions? We put in some large-scale solar farms, where we changed and went down into the solar energy zones that Utah has and replaced cropland with kind of now dust source land to see what impacts that had. The current work we've been doing is kind of focused in two areas. One, updating the default soil properties in CMAQ. Again, using Kevin Perry's Great Salt Lake data, you can see on the right there, most of this dust sources come from these playas in Utah that are left over from Lake Bonneville. Kevin went out and surveyed all around, Kevin and team went out and surveyed all around the Great Salt Lake and those different areas. And then we've taken those properties listed down here and compared them with the CMAQ default. And you can see they're significantly different. The sand percent versus the silt and clay were quite different. The impact of that when Ty ran our emission model was to show that the vertical flux of dust being emitted as a function of the wind speed, the 10-meter wind speed. Green dots on the top are the CMAQ levels. The cluster of other dots down below are based on Kevin's data. And you can see that's about half. We're getting about half the amount of dust emitted with those updated properties. The second area that we looked at was adding non-photosynthetic or brown vegetation fraction. This was developed by Hossein Faratun and his student Xinyue Huang over at Virginia Tech. They're on a subaward to BYU working on this project. So on the right-hand side there, you can see some work Xinyue did in the western U.S. where she looked at the green dash is for what you would call green vegetation, photosynthetic participating stuff. This is a chart of January through December. Obviously low green vegetation. Think of Utah, wintertime, not a lot of green vegetation. Then as spring, summer comes, we ramp up, there's more of it, and then it decreases again in the fall and winter. The brown line is the brown vegetation, non-photosynthetic vegetation. And when we include that, you can see that's a significant amount of coverage. So what that essentially, well, let me step to the bottom graph. On the bottom, I'm showing the fraction of vegetation-free erodible lands. How much land is available that will generate dust? And if we consider only the green vegetation, on the left-hand side, you see the dark red areas, high fractions. 0.8 to 1. A lot of the land is available, particularly on the western side of Utah, that is available for erosion. If we put in the brown vegetation fraction there, we've covered a lot of that. We've reduced that available land for erosion, and therefore we expect the dust emissions to decrease. So we reduce the NPV reduces the amount of erodible land. It also reduces the wind drag that gets down to the soil and blocks it. So again, inhibits the interaction between wind speed and the actual surface, which mitigates the dust emission. So both of those things tend to reduce that. So both our property update and the NPV results suggest that our default modeling CMAQ was over predicting dust emissions. So we're seeing things that are lower than that. In the future, we want to add a crust model, develop a crust model to look at that. And then also we want to look at weighted averaging of properties. One of the significant challenges we have in modeling is we're modeling areas with 4 kilometer or 8 kilometer squares. But we know the properties vary significantly, that areas emit dust, areas have shrubs, and so we take these big pieces. How can we appropriately weight the properties to say this is representative of this area in terms of dust emission? So we want to do work in that on averaging those properties appropriately. All right, I want to talk deposition now. So I mentioned we track speciated mineral elements, calcium, sodium, aluminum, iron, lead, etc. And we're going to track from the emission, transport, and deposition of these speciated elements. We look at dry and wet mechanisms, and I'm not going to talk about those in detail due to time constraints. It's transient, so we can look at how it's moving through an event. We can see a snapshot in time, or we can say, what is it cumulative over a time period? We can look at a week, a month, a season, if you will, to see what we've done in terms of a deposition of a certain mineral in an area. And we can look at it statewide, we can look at local points, or we can look at watersheds and see how much was deposited in a watershed. So I'd like to illustrate those with some of the results we have. On the left is a dust event. It looks like a dust event, right, happening. So PM10, this is kind of a north to south event, primarily on the western part of the state. So it's not really one of those west to east, sweep across the mountain and the valley sort of things, but is more of a north-south. You'll notice we start off at this is September 7th through 9th, 2020. We start off a lot of activity in the north near the Idaho-Utah border. And then as we move down, we get additional dust that's generated and carries down to the middle part of the state over here. So now on the middle upper, I'm showing the sodium volumetric emission rate. This is the amount of sodium that's come off and is in that first layer as a function of time. And this is a snapshot in time. This is 6 o'clock UTC on September 8th. And you can see, boom, here's the sources. Here's where it's coming from, and I've chosen sodium here throughout this illustration, but it could be whatever element we wanted. And that tells us what's coming up. Next to it on the far right, I'm showing the concentration, mass per volume in the atmosphere of sodium. Some of that's come from that specific emission. Some of it has occurred previous to that and has been transported around. So that's a snapshot that said, here it is spread all over, concentrated from those emission sources, but also in a time period that may have happened before our 6 o'clock snapshot. Okay, we combine that, and then in the lower left, we're saying, okay, here's my snapshot of what deposition, how much sodium is being deposited right now. Mass per area at this time. And you can see we seem to be generating this stuff at the top and redepositing it, a lot of it, but not all of it. We have more deposits different than where we've emitted it that would be consistent with the fact we've got concentrations up there, and as that's falling out, we're depositing it. So we're tracking where that's going. I want to say, oh, let's look in time a little bit and step forward. Now we move 2 hours later to 8 o'clock. My deposition has shifted, not surprising because of the pattern of the event. My emission source will have shifted also a bit, and now I'm dropping out more down in the middle part of the state. So that's all dry deposition. All I've done there is with dry deposition. Want to look at wet deposition, same picture. This is sodium concentration. Okay, volumetric concentration out here with my sodium, western part of the state. Now I have rainfall going on. So now my snapshot is same time, 6 UTC, and you can see where I've got some rain. That is corresponding to where we're getting wet deposition of sodium. That moisture is actually bringing that down, depositing that, and you can see that correlates really well with the location. And it is not where most of the dry deposition was occurring. Two different mechanisms are getting that sodium out of the atmosphere down onto the surface. You can see the linkage here. when I take the sodium that rainfall comes through, deposits it, I've basically taken it out of the atmosphere. And if I move forward in time, the rain with the fronts moved down a little bit more in central Utah. So is the wet deposition. Now I'm depositing stuff in these snapshots. And we could do a GIF of those and watch how that progresses over time. Okay, so that's kind of the snapshots in time, the pictures. Now, the question is, what do we do if we can accumulate that and put it in watersheds? So on the left here is a picture of the Utah watershed basins, the major ones, some of the sub-basins. We've plotted this in the sub-basins, I think 67, Ty, 37, 67, I can't remember.
67 for AGC8.
Okay, 67 subdomains. And so what we've gone in is said, in a period from September 1st to 9th, how much sodium was deposited in each watershed during that time period, that cumulative value. So we've got Curlew value. This stuff was coming from early in the storm. We saw the events happening initially up there, and then the storm kind of came down here, and we had some other stuff. So a Tule Valley watershed, a Sevier Lake watershed had high values as some of the others, and then lower amounts over here, dry deposition. This is our dry deposition map. Wet deposition is on the far right. And you can see it's in a different location, right? Different mechanism. That's where the rainfall was. That's where wet deposition was. So we have cumulative values over there. And the Spanish Fork and Sand Pitch watersheds have higher values there. And then we can combine those and show total deposition in a watershed. So it kind of makes sense what we're doing here. Got a location of interest in a watershed, how much minerals are going in there for whatever time period we want to get a cumulative value. Yeah, I'll skip that. Okay, so this was a slide that I think Mackenzie Skiles put together back in our reverse site visit. And she kind of said, we want this systems model thing, and then she listed all this stuff about all these topics about dust. And what I tried to do here was note in red all of the areas that the model touches. All the areas that the model can link to. Here, that we've done in dust emission, yeah, we've done surface type, we've done particle sizes, we've done vegetation cover, land use changes, disturbance Mark talked about. We have not, in our model, talked about drought and climate change yet. You could do it, you could get there, we haven't done it. Emission likelihood, weather stuff, certainly, with modeling with WRF and stuff. Then the post-deposition, the snow melt, Derek talked about how we can track and put dust on snow melts with models, right? We can do that and say, here's how much is deposited on a snow melt over whatever time period we want and whatever distribution from all the sources. Emit all those sources across the state, track all the weather events, put it down to get a cumulative value to say how that's affecting the phenology, seasonal behavior we can look at. And what's really exciting now, I think, is this idea of taking elemental stuff and putting it into the water nutrients, right? We can feed this into a SWAP model for a watershed. And compare that kind of stuff. Look at nutrient cycling, look at the eutrophication. And then last category, we have not done, I have a little kind of orange thing there, and we haven't really done that. You could look and say, oh, I deposit this stuff on the snow and it's mostly iron, so it's darker. It's mostly calcium, it's lighter, so it affects the radiation absorption on the snow. We haven't dealt with that. Okay, so next steps. We want to continue to improve our emission predictions. We want to refine the composition and our elemental inputs from the Utah Playas, and then add our future crust modeling and weighted averaging. We want to compare speciated deposition predictions to filter samples and water measurements. Right, the classic thing is, okay, we're going to take measurements, we're going to do models, and we're going to compare the results. And if you're a modeling person and the results don't match, you throw away the experiments and you write your model results. Right? And if you're an experimentalist in the model results, you throw out the model results and then you just look at your experimental data and you do that, right? But if we really want a predictive model, we've got to get the right physics inside the models to be able to use it for predictive. And that's where models are really powerful, right? Stuff that happened, okay, it's historical. We try to understand it's good. But what we'd really like is predictions and ability to do that. And we've got to get this validation right to be able to do that. And then, okay, now what do we do for linkage? You know, how do we link the water quality, the model results, the nutrients? We can do different time frames. What are those of interest? What are the time frames of interest? What are the spatial resolutions of interest? What could be useful to the other research areas that people are doing that we could use this elemental information for? I think I'm done. All right, thank you.